Good morning, students. You are most welcome in next video lecture of the Department of Chemistry, L&T College Multimedia Studio. So, today's my topic is cryptates, new dimensions in coordination chemistry. So, what is the cryptates and how this is derived from the crown ethers? So, the chemistry of crown ethers and cryptands, they are basically correlated with each other, right? So cryptates, if you are talking about the crown ethers, so crown ether is nothing but, as you know previously, that it is a macrocyclic ligands. So it has a monocyclic ring, right? So this is actually 18 crown 6. So that is a crown ether, and the cavity size of this crown ether, so this is the cavity size, right? So this is the cavity size of the crown ether, 2.60 to 3.2 angstrom, right? So the size of the hole, so that is what we call host, lie in this range, and this is monocyclic ring structure, right? So this ring is composed of actually oxygen donors, right? So as its name derived, 18 crown 6 means this ring contains total 18 atoms, and out of 18, 6 is oxygen atom, right? So the oxygen atom has a pair of electrons, that is called lone pairs, right? So this lone pair actually can be donated to the cations, right? So especially metal cation. And once the cation exists in this hole, suppose we have a alkali metal cation, so that is M plus, right? So this crown ether influence a polarization effect, polarization force, means each oxygen donor acquires delta negative charge, right? And due to positive charge on the metal, so there is a electron density on the ring, and there is electron deficiency or positive charge on metal cation. So what you expect here? The expectation is that, so there is a electrostatic interactions between the negatively charged oxygen sides and positively charged metal cation. So each oxygen acquires delta negative, right? So this delta negative, it means the ligand is actually electron rich species. So the ring, the inner part of the ring has high electron density, right? So and this high electron density comes from the delta negative charge in the inner part of the ring, right? So if the size of the cation matches with the cavity size of the this ring, then only that metal cation can be trapped by this ring structure. So suppose we have a metal cation like potassium, right? Potassium ion K plus, right? So in the form of potassium chloride. So once this potassium is encapsulated by this structure, this complexing structure. So this is the interaction K plus. So there is a complexation of the oxygen donor towards metal cation, right? Because the ionic size of potassium, so that is actually K plus is equal to 2 into 1.38. 2.76 angstrom. So this is the diameter of potassium ion, 2.76 angstrom, and this size actually lie in this range. So this 18 crown 6 selectively binds potassium cation in this host, right, and form a complex which is called crown ether complex, right? And if this potassium is alkali metal cation, actually, then potassium crown ether complex. So then the resultant complex is called potassium crown ether complex. And similarly, potassium crown ether complex, lithium crown ether complex, sodium crown ether complex can be made depending on the cavity size of this monocyclic ligand, right? So this cavity size can be changed and it forms multi-chelate rings. So this is one chelate rings, this is second chelate rings, this is third chelate rings, this is fourth chelate rings, this is fifth chelate ring, this is sixth chelate rings. So there is 6 chelate rings in potassium crown ether complex. So this complex actually is highly stable. And because of the formation of chelate ring in this structure, this type of complex actually its shape looks like a king's crown. So that is why it is called crown ether complex. So this is monocyclic, and because of the formation of the chelate ring, so the structure gives a crown shape. So apart from this crown ether, so another class of organic ligands, so which contains actually two nitrogens at a bridgehead and which is bridged by polyether ligands, right? Polyether strands. So that is what we call it as strands. So this is polyether strands or strains, right? So this is the nitrogen atom, this is the nitrogen atom. Here two cyclic rings are present. So first ring is this. So this is the first ring and this is the second ring. So this structure is also similar to crown ethers, but it contains two hetero nitrogen atoms as a bridgehead, and which works as a bridging for the polyether strands. So one ring and below one is the second ring. So this is the difference. Here only one cyclic rings are present in this crown ethers, while this structure has two cyclic rings, and the name derived 222 cryptands. So the nomenclature of this ring is actually 222 indicates number of ethereal oxygen groups in nitrogen-nitrogen bridge. So 1, 2 in the first threads, 1, 2 in the second threads, and 1, 2 in the third thread. It means 3 threads in the ring structure contains 2 ethereal oxygens or 2 ether groups. So that is why its name depicted as 222 cryptand. And thus overall size of this ring structure actually lie 2.8 angstrom say 3.0 angstrom, right? So this is the size of cavity size of this structure. So what is the difference between this ring structure and this ring structure actually? So it has multi cavity sides. So this is upper one is one cavity and below one is the second cavity, right? So it can capture so more than one metal cation simultaneously, right? So this is the differences here. It can capture only one metal cation, but so this is responsible to bind more than one cations, right? So it has multi-cavity sites. So the cavity may be either bicyclic, tricyclic, tetracyclic, pentacyclic. So according to the number of ether groups present in the strands. So multi-cavity sites, such type of structure actually consisted of multi-cavity sites, right? And second one is the multi-binding sites. So it has multi-binding sites actually. And what sorts of binding sites are present in this structure? So that can be seen clearly here. So oxygen is the one type of donor sites in this structure, and two nitrogens so that are present in the structure. So they can form also complexes with the metal cation. So nitrogen and oxygen both can act as a donor sites in this structure. So it is nothing but a hetero bicyclic ring structure, right? So it can accommodate not only nitrogen and oxygen. So the replacement of either oxygen or nitrogen by the phosphorus or sulfur atom also can be adjusted in this ring structure, and they also act as a donor sites. So it is a wide spread structure, so beyond the crown ethers, and multi-binding sites. And third one is the multi-complexation mode. So it has actually uh, two cavities in case of this 222 cryptand. So sometimes maybe it form complexes with the complex formation tendency of only due to oxygen atoms, right? So and maybe nitrogen do not bind with that metal cation. So this is the possibility. And another one is the possibility is that it may only accommodate one binding cavity. So it may be one cavity can accommodate metal cation, while another cavity may remain vacant. So there is a different types of complexation tendency with the metal cation. So in this structure, right? And it is actually dicyclic rings. So as previously I have dictated. And another one is a heterocyclic ligand. So it is heterocyclic because of presence of oxygen, nitrogen, and carbons. And what other uh, things is important in this structure? As you have seen that, so inner part is hydrophilic, right? So it has a inner hydrophilic layers and outer in the exterior part. So there is a hydrocarbons CH2, 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 CH2 like that are present in the exterior of the rings. So this methylene, two methylene groups or CH2, CH2 will act as a hydrophobic groups. So this crown ethers actually contains hydrophobic as exterior and hydrophilic as interior of the ring. So it has dual natures and it can behaves according to the nature of the coming reagents or solvents. So interior salvation cell is due to the electron rich oxygen centers, and exterior salvation cell is due to the presence of hydrocarbons and as a hydrophobic sites, right? Similarly, in this structure also, in the interior part, so there is a hydrophilic cavities, and in the exterior part, so there is a hydrophobic environment. So that is due to presence of methylene group in the ring. So this is the similarity between crown ethers and cryptand. And what is the meaning of cryptand actually? Cryptand comes a Greek word called kryptos, which means hidden, or you can say it can capture the cation and hide it completely. So the name derived cryptand, right? So it forms cage-like structure actually. So this is cage-like structure, cage-like structure it can forms, and it forms multi-chelate rings during the complexation. So the stability of such type of metal cryptates comparatively very high compared to this 18 crown 6. Here one monocyclics contains 6 chelate rings. Here two cyclic rings contains more than 6 chelate rings, right? So larger the number of chelate rings in the structure, so greater will be the complexation behavior and the stability will be very high. If this cryptand will react with the metal cation or with a salt of ionic compounds, so that forms metal cryptate complex. So that is the formation constant Kf, and Kf for this cryptand when it is captured by the metal cation forms metal cryptate is very high. So formation constant of such type of complex actually is very high compared to the this crown ether complex because of the large number of chelat ring in this structure, right? So the size of this ring lies 2.8 to 3.0 angstrom. So if the size of the metal cation lie in this range, so that can be captured in this ring structure effectively, strongly. So selectivity of the metal cation depends on the size of the cavity, right? If the size of the metal cation matches with the size of this ring, then only it can form metal complexes. Otherwise, it cannot form metal complexes. So, if the size matches with this window, then it can selectively bind with metal. So, suppose if it has a high tendency to form complexes with potassium, right? So, potassium plus, because the diameter of this potassium plus is 2.76, which realistically lies in this range. So, it conforms complexes with such 222 cryptand. So, it conforms like K222 cryptand, right? So, this is plus, and if there is counter anion, that is Cl, so that can be adjusted in the structure. So metal cation may be in the form of salt. So suppose that is KCl, so which contains K plus and Cl minus. So this is called cryptate complex, right? So once potassium ion is captured by the ring, then it is called cryptate complex, and outer sphere is balanced by chloride anion. So overall, this is what K222 cryptand, and in full bracket Cl is outer side. So because of presence of hydrophobic solvation cell in the exterior of this ring, the Cl minus ion does not solvate it strongly through the hydrophobic structure. So they will remain active in the outer part of the ring, while this potassium is deep inside this structure. So they are strongly solvated through the hydrophilic structure of this cryptand. So potassium ions selectively binds with this cavity, and they are not free. So it forms very stable complexes, right? So the stability of the uh, metal cryptates are very high compared to the stability of the metal crown ether complexes because of the structural diversity and its stability, right? So now, what is the beauty of cryptands? So cryptand is nothing but a class of organic ligands, so that contains two nitrogen atoms, and actually they are bridgeheads or bridges by a threads of polyether ring, polyether thread strands. So it can form bicyclic, tricyclic, tetracyclic ring in the structure, and the cavity size can be varied through the functionalization of the carbon centers or hydrocarbons bond. So suppose there are various types of cryptands are present in the chemistry. So suppose we have two 1 1 cryptand, right? cryptand and 2 to 1 cryptand, and that is 2 to 2 cryptand, and another one is cryptate is structure like that. So this is actually so 3 to 2 cryptand. So we have collected from the reference 3 to 2 cryptand, right? So and the size of this cryptand 1 point cavity size 1.60 angstrom, and this size of this cryptand 2.20 angstrom, and the size of 2.80 angstrom, and finally it has 3.60 angstrom, right? So this is the one cryptand, and this one is the second cryptand, and this is one third cryptand, and this is the fourth cryptand. So we have a four cryptand structure, so that contains different numbers in the square bracket. So what do you mean by this? It means this cryptand actually contains in the first strand two ethereal oxygen group, in the second strand only one ethereal oxygen group, and in third strand there is only one oxygen or ethereal oxygen group. So if the number of ethereal groups or oxygen groups between two nitrogen center is low or small, its cavity size will be low. So here total ethereal oxygen 4. So only 4 ethereal oxygen groups are present in this ligand. Here 5 ethereal oxygen group. Here 6 ethereal oxygen groups. Here 7 ethereal oxygen groups are present in the cryptand ring structure. So depending on the number of ethereal oxygen groups present in this cryptand, so the cavity size can be produced or generated in the structure. So if the size of this cryptand is 1.6 angstrom, it means it can bind lithium plus, because lithium plus has diameter 2 into 0.76 angstrom size. So lithium plus has its diameter 1.52 angstrom to that of the cavity size of this ligand 1.60 angstrom. So this cation can be captured effectively by this cryptand. So no other cations can form complexes with this ligand. So it totally depends on the match of the cavity size to size of the alkali metal cation. And similarly, this ligand has little larger cavity size because of the increased number of ethereal oxygen groups. So it can form complexes with sodium cation, right? And similarly, it has 6 ethereal oxygen group between 2 nitrogen bridge heads. So the cavity size of this ligand actually is larger than that of the previous structure. So it can encapsulate uh, potassium ion effectively in the structure and stabilize the complexes, right? And the fourth one is a structure having 7 ethereal oxygen groups and its size is 3.6 angstrom. So it can bind even rubidium, even cesium plus also, right? So cesium plus is the bigger cation while lithium plus is the smaller cation. So it has a diameter 1.72 multiplied to 3.44 angstrom. So this cesium has 3.44 angstrom its diameter. So that can be fitted in this structure. So you can say here the cryptand can selectively binds metal cation. Not every metal cation can be complex with the particular cryptand. So it will totally depends on the size match of the metal cation to that of the cavity size of the cryptand. So this is the beauty of the uh, cryptand. Suppose we have a cryptand like that. The basic structure of the cryptand as we have previously shown. So that is one oxygen, nitrogen, and this is oxygen, and this is nitrogen, right? So this is your right. So suppose so this is your so this is your that is 222. So this is the structure, right? 222 cryptand. So it can forms complex with potassium ion because its size 2.80 angstrom, right? So what is the chemistry and in what other ways we can increase the cavity size in cryptand? We can simply apply the chemistry and we can tune the cavity size through the functionalization of the hydrocarbon chain. So if this carbon carbon if this carbon carbon is functionalized with benzene ring, right? So suppose this carbon carbon bond and this carbon carbon bond is functionalized symmetrically with two benzene rings, then its cavity size does not remain 2.80, rather it changes. It may be it may be chance of either the cavity size may be decreased or increased depending on the substituents present on the exterior of the hydrocarbons. So there is a possibility that so there is a functionalization it can occurs. So here we can insert either electron donating groups on the exterior of the hydrocarbons or electron withdrawing groups like NO2 or electron donating groups like amine, so the cavity size can be changed. So in this way the functionalization can change the cavity size of the this cryptand, and on the basis of, or once the cavity size is changed, so it has a capacity, it has a large affinity to bind different metal cation in the solutions. So it can forms different structure with binding of different metal from the solution. Suppose we have a solution having different metal cations. So if you add this choosing cryptand structure in the solution, so it can capture metal cations, only those metal cations which diameter matches with the its cavity size. So this is the beauty of complexation and in the coordination chemistry. So it perfectly hides, or you can say cryptand completely wraps around the metal cation and protect it completely, right? So this is the way you can differentiate the complexation tendency of the cryptand with that of the crown ethers. So this is the beauty of the cryptand actually, right? And this cryptand, another beauty is that this cryptand maybe have a greater affinity to forms inclusion complexes, right? It can form inclusion complexes, inclusion complexes, right? So it can form inclusion complexes, okay? And it can accommodate, so this structure is susceptible to accommodate actually either cationic species, so cationic, anionic, or neutral organic molecule, neutral organic molecule. So this is the another advantage of this cryptand. It can accommodate so cationic species, anionic species, and neutral organic species. So sometime apart from this structure, we have a borocryptands. So borocryptands is actually anionic in nature. So that can selectively binds with chiral organic molecule. So it can form complexes with the chiral molecule also. So this will increase or enhance the scope of the organic chemistry also, right? So another one is that it is lipophilic in nature, right? So such type of ligand is actually lipophilic in nature. It means it can bind lipids or fats in its host, because cryptand and cryptate chemistry is based on host guest interaction. So any guest, so that is lipid or fats, that can be fitted in this host, right? So depending on the selectivity of the cryptand. So this is the beauty of this structure, right? So what is the lattice energy of the cryptand? Uh, Lattice energy of the cryptand, actually you know that lattice energy in kilojoule per mole, right? So lattice energy, as previously we have defined the energy which is required to break a 1 mole of ionic compounds. So it is called lattice energy, or when 1 mole of ionic compound is formed through its gaseous cations and anions is called lattice energy, and which is in kilojoule per mole. So in case of metal cryptates, what is the uh, lattice energy and what sorts of information we can get? So that will be actually lattice energy of cryptates. Suppose we have a data that I have collected K222 cryptand Cl and yarn A222 cryptand Cl. It has lattice energy around delta U is equal to minus 550 kilojoule per mole, right? So this structure has only delta U minus 450 kilojoule per mole. So and this is the beauty of this cryptid structure. So because of the size of the cavity, so the lattice energy can be produced, and because of the electrostatic interactions and structure of the cryptands, so that can be obtained. So suppose in case of potassium, this is the potassium cryptate and this is the sodium cryptate complex, right? So the due to the electrostatic interactions, so here this is positive charge and this is negative charge. So the lattice energy is actually minus 550 kilojoule per mole, right? And here 450 kilojoule per mole. Why this is comes? Because of the size of the uh, cations. So potassium plus is larger than that of the sodium plus. There should be little low lattice energy comparison to this. In case of simple ionic salts, but in case of cryptane, there are variety of structural segments present in the structure. So here normal trends does not found. In case of potassium 222 cryptane, uh, lattice energy is 550 kilojoule per mole. To that of the sodium, similar cryptate structure 450 kilojoule per mole. So here 100 kilojoule per mole is less. So this is the actually because of the structural diversity and variation in the cavity size due to presence of metal cation. So what actually you can inference here is that, so once the alkali metal forms uh, a complex through cryptand structure, so the lattice energy actually decreases. So all alkali metal cryptates have low lattice energy compared to normal ionic salts. So normal ionic salts follow some trends as the charge and size of the cation and anions and interionic distance. But in case of cryptand, actually interionic distance is very, very large. So suppose this is your cryptand complex and this is your chloride ion. So this is your K plus. So this is the distance. So this distance is actually very large, and because of the presence of complexation cell, because of the presence of wide complexation cell in the cryptand structure, so the distance between this cryptand complex and outer anion, that is chloride ion, is very large. So the lattice energy expected to be low. So, and because of low lattice energy, so it can be easily solubilized in any other solvents. So this is the beauty of the cryptands. So they can be solubilized in organic or inorganic solvents because of the low lattice energy. So now the application parts of the alkali metal cryptates can be actually uh, explained in the next part of the video. Thank you, students.